Let's learn section 3.2, measures of spread. Now that we've learned the various measures of center, mean, median, mode, let's take a look at a measure that determines the spread of the data, which I personally think measures of spread are criminally underrated in everyday use. And one of the things that separates a statistician from just a regular observer is understanding measures of spread. And let's take a look at example 1, which I ripped from the book because I think it's such a beautiful example of the importance of spread. Look at the average monthly temperatures for San Francisco and St. Louis over a calendar year. Do they have similar weather? Well, if we take a look at the data using certain measures, we might get one conclusion. And if we use certain other measures, then we might have other conclusions. So, for example, if we look at measures of center, I entered the San Francisco weather into the Excel app that's available in my classes. And note that the population means 57.5 degrees, and the same as the sample mean, whichever, it's the same thing. But anyway, the median is 58, right? So pretty standard stuff. Mean's roughly the same as the median. Let's just write this down. I'll call this X bar San Francisco. This is sort of a sample after all. Is 57.5 degrees Fahrenheit, if you care. The median for San Francisco is 58 degrees. Okay. And while we're at it, why don't we go ahead and just take a look at a graph, a histogram of that, right? So right here, we have this guy. Let me see if it pastes nicely into good notes. There we go, right? A little thing right there. That's San Francisco, right? Just go like that, okay? So we have that. All right, now let's do the same thing for St. Louis. Okay, this will just take a sec to enter the data. I'm going to go back here. Whoop. Just delete contents. And we're just going to re-enter the data, but this time I'm using the data from the bottom row. And maybe you even see. So I'm entering the numbers. Maybe you have an observation. Just looking at the numbers. I may have missed a data point. Hold on one sec. 30, 35, 44, 57, 66. Whoop, sorry about that. Missed 75. Whoop. All right. And now let's take a look at this. Here, the mean for St. Louis is, well, it's not exactly the same, but it's 56.1 degrees. That's basically the same thing. And in fact, the median is the exact same thing. It's still 58 degrees. And if we take a look at the graph, let's see what happens if we graph this data. Just copy this stuff, go on and paste it in the quantitative graphs at the histogram. We want to fix our lower and upper class limits so we sort of get a sense what's going on. Whoop. Annoying. Hold on one sec. Well, for some reason it's not letting us. Let's try that one more time. Copy. And then we paste. Please let us paste. No, it's not going to do that. Awesome. Anyway, I guess we have to enter the data in again. Whatever. Enter this in enough times, I'll memorize what the temperatures are. And maybe you can see as I'm entering things in that we have a pretty different histogram that's going on here. Let's copy this guy and paste this right here. right? And this we will lovingly label as St. Louis temp, right? So these graphs are very clearly different, but maybe there's a measure we could use so that we don't have to graph the data. Can you think of one? Well, one thing, if you thought about it for a second, is you could look at the range of the data. The range of the data is the highest minus the lowest value. So I'll say the range equals highest minus lowest. And here I think we will see some difference, right? Because the range for San Francisco is going to equal, what is it? You can just kind of look at this. The highest is 63. The lowest appears to be 51. 12, right? 12 degrees. Okay, whereas the range for St. Louis equals, I guess, 79 minus 30. And that's 49 degrees. So that's a pretty basic way of saying, hey, look, this data has quite a bit of range going on. There's a big difference, right? One is ranging from like middle of the road to middle of the road. The other is ranging from freezing to hot. Okay, so this is definitely a basic measure we want to keep in mind. But I think there is a more deep measure of spread that we can talk about. And I want us to just derive it. Well, not derive it per se, but I want us to define it. The mathematical measure of the amount of, I guess you could talk about, of the spread in a data set is the standard deviation. If you take one thing away from this class, make it an understanding of the standard deviation, because we all know that you understand measures of center, mean, median, mode, right? We know you understand that. So try to understand the standard deviation. This is very, very useful. This will separate you from the other people. This is what will make you a statistician, and they'll just be observers. So anyway, to calculate the standard deviation, we first write the formula for its square, the variance. And this gets a little bit technical here. We have that the variance, so I actually have to write two formulas here. I'll say population variance equals the following, equals this lovely formula. It is going to be, I guess we'll assume, given a data set, x1 through xn, right? N distinct values. Okay? So this is going to be x1 minus the mean, or I guess I should say minus the population mean, and then we square it. So the difference between each value on the population mean, and then we square it, right? Plus, and we do the same thing, and then we get the same thing with the last one. And then we take the average of all this. Okay, we just divide by n. Okay, now you might see this a little bit more compactly written like this, perhaps in the book. You don't have to worry about it, though. Don't worry about that. I'm just writing that there for fun, okay? That's the population variance, okay? And so the population standard... Oh, shoot, you know one thing? Yeah, actually, I'll do this first. Yeah, so the population variance, sorry, just one thing really quickly. I do want to write the notation for it. This is sigma squared. That's a lowercase sigma, right? Greek letter for S. So anyway, the population standard deviation is going to equal sigma, which I hope you can see that's the square root of sigma squared. Maybe I'll write a little bit lower. And this is going to equal, well, just the square root of all of this. Gonna be a little bit lazy there, right? And just do one of these guys. And maybe I'll shrink it just so it fits. Okay, much better. right? So you just take the square root of all that. All right, and then this is the same, of course, as the square root of, yep, you guessed it, that guy. All right, it's the same thing, okay? Just to be clear, that radical dips down. It covers the n as well. Okay, so anyway, two terms here. This is the population variance. This is the population standard deviation. You might say, wait, Dr. Halpern, why did you define both of those terms? Well, because there's also a sample variance and a sample standard deviation. I'm actually going to use a different color just to highlight this. The formulas are very simple, and I will just promise you right now that you will never need to manually use this formula, ever. We let the computer do it, and that's the end of that. Still, we should at least see it to know what we're talking about. So the sample variance equals S squared, right? English, right? Remember, Greek for population, English for sample. And we're going to get, so now we're assuming we have a sample of its size n. Same thing, but remember that when we talk about the sample mean, we refer to it as x bar. Same thing here. So remember, mu and x bar, they're both the mean. It's just whether you're talking about a population or a sample. Here's where it's different. It's n minus 1. You divide by n minus 1. Okay, and so what happens here is we... Oh, actually, no, sorry, we don't have square roots yet. Sorry. What happens here is we just have this sum. Again, don't even worry about this. I'm just putting it here for, the sake of completion. Okay. This is the sample variance. And you might guess what the sample standard deviation is. This equals S, which equals the square root of S squared, right? So just find the variance, take the square root of it, and this equals, oh boy, let me maybe lower this a little bit, all right? Okay, and this is going to equal the square root of, all this junk right here, right? It just like you might just as you might expect. Let's lower that by quite a bit. There we go. Very nice. Really, really fit it in there. Excellent. Great. Okay. And then this, of course, equals square root of this guy. There we go. Right. Awesome. So those are the formulas. Now that I've written them down, just want to point out that we're never going to use them. But the computer uses them. But I want you to understand what the computer is actually doing, okay? We will never use this by hand. But we should know what it is, okay? Now, I just want to point out that unlike the mean, or median, or mode, frankly, the population and sample variances, and hence standard deviations, have slightly different formulas. Now, the real reason is technical, but the book gives a nice quick little explanation, right, which is that sample data tends to be less varied than population data. And so that might mean that the sample variance, sample standard deviation might be a little bit artificially lower than it should be. So the way to account for it is divide by a slightly less, less number, lower number, which kind of raises it a little bit, kind of puts it a little bit more in line with the population standard deviation. And to be a little technical, you say you're using one less degree of freedom. If this explanation does not satisfy you, well then great. Read the book. Perhaps it might give you a better, more in-depth explanation. If that still doesn't satisfy you, then become a math major with statistics concentration and then take math statistics. Anyway, let's find the standard deviation of the temperature data in example 1. Let's go back up to this first page. Right? Now, actually, if we go to the Excel file, I think we already have the St. Louis stuff in mind. Oh, I hope it kept our data. Oh, it sure did. I think we go to descriptive stats, it should still be there. What about the sample standard deviation, which let's use the sample one. We have 17.85, let's say. So one common convention is that you round to one more decimal place for the standard deviation than you do for the mean. So we'll say the standard deviation for that was St. Louis equals 17.85. All right, now let's find the sample standard deviation for San Francisco. Just means we have to enter the data in again. So I guess we should pull this up one more time, and we are going to have oh, 63, and I think it was 58 and 52. No, I think I. Oh no, you know what I missed? I missed 62. Hold on a sec. Not 82, 52. There we go. Okay, and now here, if we take a look at the sample standard deviation, whoa, that's quite a bit different. 3.92. So that's what it is. Oh, and by the way, in case you're wondering what the unit is, it's the same as it is for the mean. The variance is degree squared. That's kind of weird, but standard deviation is just the same as before. Okay, so here, this is a good measure of spread, right? Because we see much lower, so less spread. And this guy, much higher, so more spread. Right, so basically the further away it is from 0, the more spread is in the data set. Okay? So this is a good confirmation that yes, in fact, our eyes do not deceive us. The St. Louis data is in fact much more spread out than the San Francisco weather data. Okay? Now, just one thing you might be wondering. Why does the standard deviation formula involve squared distances from the mean? Now, the reason is technical. I don't want to get into this too much, but just the basic idea behind this is that, oops, sorry for these notifications here. The basic idea of this all is that we want deviation from the mean to be significant. We want it to show up significantly in our measure. And you amplify that deviation by squaring the difference between that data point and the mean. So I'll just say that I'll say properly amplify the, how should I say this? Probably amplify the variance, or I guess I'll just say the spread of data. We square the absolute value of just xi minus mu, or minus or x bar. Right, so we don't care whether it's positive or negative deviation, we just care that it's deviation. So that more spread quickly, I guess I'll just say quickly, leads to a higher S or S squared. Okay? So that's why. So as I mentioned at the start, standard deviation is extremely important, right? The standard deviation gives context that the mean might not provide. Again, if we just took the mean of our data, we wouldn't have understood the full picture. So one nice thing about standard deviation, it gives us an idea of how close, we'll say, most of the data is to the mean. Now, at this point, I'm going to go ahead and skip this part because we skipped this part. So just go ahead and X this out in your notes. Please go ahead and X this out on our notes. Awesome, thanks. Okay, now we're going to get to something very, very important here. In a little bit, maybe a week or so, we're going to learn about the most important distribution of data, the normal distribution. We'll do all sorts of things in the normal distribution. For here, we're just going to look at a snapshot. The shape of the normal distribution is a bell curve, a mound. Most data accumulates near the mode, which is also the mean, which is also the median. But of course, the mode is the highest frequency. The ends have, I guess you'd say, I guess I'll just say sparse data, not a lot. And the shape is unimodal. If our data is approximately normally distributed, so if it approximately, if it has a rough mound shape, then we know the following. And let me actually get out a nice image from Desmos. I can illustrate this nicely. Here we go. Take a snapshot of this, and I'll just copy paste it. Don't worry about the numbers on the bottom so much. Okay, we're just going to copy this guy. Make that nice and big. Okay. So what does it say? It says that roughly 68% of the data is within the range mu minus sigma to mu plus sigma, or is within the interval rather. Okay, so that's if this right here is mu, like the center of the distribution is mu, then this right here is mu minus sigma, and this guy is mu plus sigma. Okay, and that is roughly 68% of the data. Okay. If your distribution is roughly normal, and you want to know about two standard deviations, it turns out roughly roughly 95% of the data is within the interval mu minus 2 sigma to mu plus 2 sigma. Right, which is here to here. Right, roughly 95% of the data is within this interval. Right, including that blue area. Okay, including that blue area. And then, yes, if we considered the green, then we have that roughly 99.7% of the data is within mu minus 3 sigma to mu plus 3 sigma. Okay, so I guess I'll just do one more of these guys. This is 99.7% total, including the red, including the blue, right? So almost all the data is within 3 standard deviations of the mean, okay? Now, I just want to write this right here is within 1 standard deviation of the mean, right? And this is within 2 standard deviations of the mean. And this is within 3 standard deviations of the mean. Okay? So all this is to say that most data in normal distributions, which again is a lot of what we're going to be working with, falls within 3 standard deviations of the mean. Now I just want to note these approximations work only if the distribution is approximately normal. Okay? So let's look at the data in example 1. Is that approximately normal? Well, kind of for San Francisco, maybe a little bit. Maybe not so much for St. Louis. Okay, a little all over the place. I'll just say. Okay, I'll just leave that to you. So here's a question: what happens if our data is not approximately normal? Or maybe we're not even sure about the distribution, but somehow we do know the mean and the standard deviation. Well, it turns out we have this beautiful tool called Chebyshev's inequality, which says the following: for any distribution, normal or otherwise, it could be binomial, bimodal, skewed, uniform, whatever it is, the proportion of data within k standard deviations of the mean is at least 1 minus 1 over k squared. So, for example, 1 minus 1 over 2 squared, that's a 2 squared, which equals 3/4 of the data, or, of course, 75% of the data must be within 2 standard deviations of the mean. And 1 minus 1 over 3 squared, which is 8/9, which is roughly 89% of the data must be within 3 standard deviations. Okay? So let's take a look at some baseball data. Okay? This will be the last thing we do. So if we go to Fangraphs over here, I need to reload it for a second. We take actually, you know what? We take a look at the batting average data for the leaders. I think I've gone ahead and already copied that into Excel. Might want to get that up. Let's see for a sec if I can, if it will load. If it will give us our recent files. Hope it will. Maybe not. Maybe we need to open this one more time. Here we go. And we just click on this guy. And we go to, let's say, some kind of data. Let's look at, I don't know, batting average data, for example. Let's go ahead and select all of this. And now let's go ahead and paste it into our app. And we want to see whether or not this is normal. Suppose we're not even sure, actually. let's paste all that in there. Okay, so looking at the histogram, it actually does look pretty normal. But suppose we didn't even know that. Let's suppose for a sec that we didn't know that. We know that we're going to use population in this case because this is the whole population. Population mean is 265. Population standard deviations 22. That's how you refer to batting average. Let's actually just oh, did that? Why did I not screenshot that? There we go. Let's just do that really quickly so we have it. Okay, done. Copy and delete. Go back to our notes right here. All right, so here we're going to have that if we don't know the distribution of MLB batting average data from 2025, to be clear, is normally distributed, then we use Chebyshev's inequality to get, or I should say to see that, so I'll say first, 75% of the data, or of the averages, are within the range. So it's going to be 0.02. Yeah. Oh, it's like I think that. Sorry, I think the number I caught. Yeah, 265. That should have been 265 and 222. Sorry about that. Cut that off. Are within 265 minus 2 times the quantity 0.22 to 265 plus 2 times 0.022. Right, and then this really equals, what's that going to be, plus 44, plus 45, minus 35. I think we're getting 30, oh no, sorry, we're subtracting. I think this upper bound is going to be 309, and the lower bound is going to be 265 minus 44. I think it's going to be 221. Okay. So we know that at least 75% of the averages are within this. And of course, we could say 89% are within, and I just subtract an extra 22 from that, and I get 199, and then add an extra 22 to that and get 331. But because we know that it's normal, so I'll just say, since the data is approximately normal, we know that actually, what do they say? How much data is within 2 standard deviations of the mean? So I'll say, oh, I don't know why I wrote 3. It's just 2. So we say 1. I guess we could say 95% of the averages are within 221 to 309, and 99.7% are within 199 to 331. So it really makes a big difference whether we know that our data is normal or not. That said, Chebyshev's equality still gives us a decent range. That's all for today.